Well, welcome back after Easter break, everybody. I hope you had a great time celebrating Resurrection Sunday at your different churches. That was really just a highlight of the Christian journey to celebrate resurrection. That's what makes all the difference. And it's just a nice time, too, to have a break from school. So we're back now. We're ready. We've got 7 weeks left in the school year. And so we're in this final push towards finishing out the semester strong. We're actually going to jump to the end of chapter 5. We're going to skip some stuff in the middle, and we're going to jump to lesson 5.5. What we're going to learn about today is a similar method to what we were working on last week with rectangles, only now we're going to be working with the shape of a trapezoid, and we're going to see how that compares to what we've been doing with rectangles. But rectangles are not always the best way. So let's remind ourselves of why rectangles weren't necessarily the best. Okay, so when we looked at a rectangular approximation, we could see that there were lots of situations where we had like an underestimate. So our gap is under what it should be. And so we're missing some of the area that we need. So, we've got quite a bit of, even with doing an M, this isn't a mid. Remember that we're working on the midpoint was our last method that we did. Even with the midpoint, we had quite a bit of missing area. We also, though, have overestimates. So I'm going to shade those in red. All the places where we were over too much, the rectangles gave us more area than we needed. So the mid was the best way to estimate it that we had last week. But is there a way that's even better that doesn't give us so much waste? And so we look at if we change to the shape of a trapezoid to where the sides are different lengths. With a rectangle, the left and the right side had to be the same height. But with a trapezoid, you can have different heights. And by doing that, we have a lot less gap, a lot less waste, a lot less missing area. And so using trapezoids is even better than using rectangles. So we're going to just improve upon our method. What we need to know about a trapezoid is how to find the area of each single one. So you have from geometry the area of a trapezoid. It's 1/2 of the base, and then times the sum of the left height and the right height added together. So the two different sides, the shorter one and the taller one. And so you find those individually, and then you work to add them all up together like we were doing with rectangles to come up with a total. The trap will always be better than, okay? So it would always be better or more accurate than the 2 round methods that we had. Okay, well, I guess technically we had 3. We had left and right. I'm sort of figuring those are similar. Then we had mid. So those are the 2 round methods, and now we're moving into trap. So let's take a look at an example we have worked with earlier, but let's think of it in a trapezoidal way. Okay, so if you're given some data for this car, increments of time measured in seconds, and increments or sample values of velocity measured in feet per second. I'm a visual person, so I would more visualize this going from 0 to t, and I'd kind of work it out looking at it this way. So if I went from 0 to 7, I'm going from 30 to 36. So my scale is not going to be perfect, but we'll say I'll say that's 30 and 36 is a little higher. So this makes my first trapezoid. And so if I'm going for T1 or trapezoid number 1, that would be 1/2. The base is 7, and the 2 heights, the shorter height is 30, and the taller height is 36. And then we proceed through the different data. Okay, the next one is at a value of 12. And that's going from 36 to 43, so a little higher yet. And so now my trapezoid would look like this, and that would be T3 with a height of 43. So my second trapezoid, so plus, and then I'd be adding to that. Now my base isn't 7 anymore, my base is 5. And my shorter height is 36, and my taller height is 43. And you proceed in this manner using the data on the table. The next one is 20. So that's a pretty, it's a bigger separation between the two. And we're going to 48 to be our next trapezoid. So it would look like this, and that would be T3. So we would add to that our third trapezoid. So 1/2. This base happens to be 8, so they're not all consistent, right? 7 was our first base, 5, then 8. And then looking at our heights, 43 plus 48, adding those together. And then we would keep going. We would create the next trapezoid, trapezoid 4, so that would be going to the base of 26. And then our final trapezoid would be out to the base of 30. And so these heights come back down a little bit, going down to 44 now, and then coming back down to 40. So that would give us T4 and T5. And these are the 5 trapezoids. So we would, okay, I'm going to then add, running out of a little space here, my base of 6, and then 48 was the taller side, and 44 was the shorter side. And then my final trapezoid had a base of 4, and that would go with the taller side of 44 down to the last side of 40. And then you're going to add that up to get your total. Give you a minute. I'm going to have the sub pause the screen, pause the video, so that you can take a minute to compute that with your calculators. All right, so hopefully you've had time enough to compute that. I came up with 1,236.5. But now I want to think about what the units are. What are we answering with this question? We're comparing the unit of time to the unit of velocity. So remember, we've been working on the unit of time multiplied by the unit of velocity. So time multiplied by feet per second. And then if we do that, the science tells us that our units of time reduce. And so feet is what we come up with. And so this is a measurement of distance. The distance traveled by the car is 1,236.5 feet as our best estimate during these 30 seconds that the car was moving. As we are moving towards getting more and more exact, we introduce a new symbol. Now, some of you were asking about this symbol earlier. This elongated sort of an S symbol is said as the integral symbol. That's the word for it, okay, INTEGRAL. But you don't need to know the word so much as you need to know the meaning, okay? So the meaning means that you are finding the exact area in the best method possible. So right now, the best method possible that we have is this trap method, and we'll be finding an exact area. And the integral has different pieces that are attached to it. You always attach a lower value of a, and that tells you where to start. And so you'll be starting, okay, I'm starting at A, wherever I'm starting. B tells you where you're ending, so that gives you the interval. F of x gives you the function that you're going to be working with all the data points all scattered evenly around your function. Okay, that will be your f of x. And then d of x is just making sure you know you're working along the x-axis. And then the integral part of it, okay, that elongated s here, is telling you that you are to working to find the exact area that's trapped beneath all those boundary lines in the best method possible to you at the time. And the at the time we have right now is our best one is trap. Now, you're You're probably catching on to the fact I'm hinting that there are going to be additional methods that you'll be adding throughout Chapter 5, and each method would be getting you more accuracy and a new way of doing things. So far we've seen RAM and MRAM, and now we're moving on to trap. Okay, so here's a question where we're looking for trap 6. You can see it here. We've got a 6 annotated. And we're supposed to write an integral for that, and which means we're supposed to find the area with the best method possible to us at the time. Okay, so let's fill out the values of this integral. Looking at the value of the table, it tells me I'm working along the x-axis, starting at 0 and ending at 3. So when I write this, I'll be 0 to 3. The function is the parabola, and so in parentheses, you always put that function in parentheses. We put the formula that the table and the graph are giving for us. And then we close that parentheses and then end it with the axis that's forming the lower boundary right now. And the lower boundary is being formed by the x-axis, so you put a dx to indicate that x-axis, which means we'll be working with other things like dy in the future or dt along a time axis. We're working with dx. All right, so we need to find the area using the best method possible. And so our best method is trap. And so we'll be using a trapezoid here, and we'll try and find T1. All right, so T1 is going to be 1/2. The base is 0.5. And the two heights, the taller one and the shorter one, remember you've got the table to use here. If you don't have a table, then you're going to estimate as best you can using the grid lines on your graph. We have a table given to us right now, so that would be 3 is the taller height, and then 2.75. Okay, and then we move on to our second trapezoid. Oops, I forgot. Okay, next one, T2. That also has a base of 1/2, a base of 0.5, and the lower height is 2.75, and the higher height, according to the table, is back up to 3 again. And you proceed along from left to right. I guess it doesn't matter if you're going left to right or right to left. And we're going to create the 6 different trapezoids, T1 to T6, using the data values that are given. And we'll have T4, T5, and T6. So T3 was 1/2. The base is still 0.5. It's nice when the bases are consistent. The shorter height, maybe I'll switch colors here. The shorter height is 3, and the taller height is 3.75. And again, I'm getting those values off the table. And so my trapezoid would be 3 plus 3.75. And then T4, 1/2, 0.5. 3.75 is the shorter height this time, and the higher height is 5. Okay, I'm going to pause, have the sub again, ask them to pause the video, have you complete T5 and T6, and then come up with a total, and give you maybe 5 minutes to do that, and then we'll restart the video and you guys can check your answers. All right, hopefully you've had time to do that and check your answers and compare with your neighbors. The total for the trapezoid with 6 intervals is 13.625. Now we don't have units on this problem, so we can't necessarily say what the context of the question is. But if we did, we'd always want to check our table and then see what the units of the result would be. Now, one thing to think about is, although this is even more accurate than the methods we were using before, it's still not foolproof. It's still going to be an estimate. It is not a perfect answer. And so the question is, do you think it's going to be an over or an underestimate estimate, and why? Now, with rectangles, it was pretty easy to see where the gaps were. With traps, they're a lot closer. Trapezoids are a lot closer, so it's not quite as easy to see where what kind of an estimate it would be. We kind of have to zoom in a little farther. So what I want you to do is, let's just take a sample trapezoid. Let's take the 2 data points right here. Okay, let's take the data point at the 1.5 and above the 2, and we'll take a look at that. And I want you to sort of zoom in as much as you can. And if you were connecting those two, the curve of the parabola is curving underneath the straight line. And so the gap is right in here. And if you remember from chapters 3 and 4, that is called the concavity of a graph. This is concave up. The concave up means, I'll draw it again maybe in a different color, that the straight line that connects the top of a trapezoid is above the lower part of the curve of the parabola due to the concavity. And so if I maybe kind of zoom out and do it, I do a sample, let me see, like this, and maybe exaggerate it a little bit more, a parabola would look like this. Okay, and so because this is concave up, so because the curve of a parabola the trapezoids will always overestimate. If it's concave down, then they would underestimate. That's your reasoning, that's your rationale, okay, that's your proof. Your proof, your evidence is because of the shape of a parabola, because of the concavity of a parabola. You can really literally exaggerate it. You could do 2 dots for any trapezoid, and you can look and say, okay, a concave up would look like that. That's definitely going to underestimate. Or a concave down parabola would look like this. Okay, that's definitely on the upper end of it. So you can exaggerate for your own benefit, like for your own, just to figure out what that is. But that's why, okay? Always reference the concavity. All right, so if you were to use the best method you have so far, approximate the value of the integral below. All right, so remember, this means, this integral symbol means the best method for area that you have. We'll be starting along the x-axis. You can tell that because of the dx. 1, 2, and 2 and 3. Okay, and we'll be following the square root curve. And so square root curve starts at 0, 0, and it goes nicely through 1, 1. And then the next nicest point is 2, 4. And so it's going to look, or excuse me, 4, 2, like that. Okay, that's a square root curve. But we're only going from 1 to 3. So this is the area that we would like to use, the best method we have at our disposal right now to find the value of that. All right, so that's kind of, now you're going to declare, I'm going to use blank as my best method. Okay, so while trap is our best method, if you decide I'm going to do trap 2, now that's easy to do because it only takes 2 trapezoids, but it's not going to be as good as someone else who might decide, well, I'll do trap 4. And then I'm going to split this up into 4 trapezoids. Okay, so trapezoids are the best method, but more trapezoids will give you a better amount of accuracy. Okay, all you got to know is what these values are according to the square root. And we know that this is 1. So then we know that this is going to be the square root of 3, which will be a decimal value. This will be the square root of 2 as a decimal value. If you decide to do trap 2, that's all you'll need. So you would have, okay, my first trapezoid, if I'm only, would be 1/2. The base from 1 to 2 is 1, and the heights are 1 plus rad 2. And then the second trapezoid would go from 2 to 3, and that would have a base of 1, and the heights would be rad 2 plus rad 3. Now, if you decided, okay, I'm going to be more accurate, I'm going to do trap 4, well, then that means that you're going to be adding data points in this individual spots. So you'll be looking also at 1.5, and you'll be looking at 2.5, which will give you additional height values, the square root of 1.5 and the square root of 2.5, and that's going to be even better and more accurate using your calculator. And so your traps would say, okay, mine are going to be 0, and I'm going to have only a base of 0.5, and my heights would be 1 plus the square root of 1.5. And then my next one would be 1/2, a base of 0.5, and then my next heights would be square root 1.5 and square root 2. And then 1/2 times 0.5, and my next would be square root 2 plus square root 2.5. And my last trapezoid, my T4, would have a final base of 0.5 and would be square root 2.5 plus square root 3. And then you use your calculator to evaluate that. That will give you an even more accurate result. Now, usually it'll be specified for you how many you need to have, okay? Would your answer be an over or an underestimate? Well, we want to look at what the concavity of this curve is. This square root graph is concave down. And so anything that's concave down with a trapezoid is going to, the traps are going to be underneath, okay? So see if you can picture that. If I have a trapezoid here, and I'm going to exaggerate it, and I have something concave down, a curve that's concave down on top of that, the trapezoid is underneath the curve. So this would be an underestimate. And the reason is because the square root graph are concave down in their curve, their curvature, their nature is concave down. All right, so that's your introduction to working with trapezoids. You'll have some trapezoids that are going to be on a graph. You'll have some trapezoids that'll be made off of a table, and they'll have some trapezoids where you'll be given just the equation, and then you need to create either a graph or a table. Totally up to you how you want to do it. If you want to make a table of values and do your trapezoids that way, if you want to draw the picture, so you'll use your best method. All right. Please stop by, send me an email, let me know if you've got study halls in your schedule or want to stop by before or after school. If you are having trouble, we're going to have a quiz on the different methods, the rectangles and the trapezoids, on Friday of this week. All right. I hope you have a good start to your week. I'll see you guys later.